Hi, everyone. Thanks for coming to this session. This is the session on fairness and diversity. We will be starting with our first paper, where Anelia Ovella is going to be presenting on I Am Fully Who I Am towards centering transgender and non-binary voices to measure biases in open language generation. I'll hand it off to you.
All right. I'm going to be doing similar Queer and AI approach of getting my speaker notes organized here. All right, cool. Hi, everyone. My name is Anaelia Ovadje, or Elia for short, and I use they, them pronouns. And today, I'm going to discuss some work done with some colleagues at Amazon last summer, Amazon Alexa and their Global Diversity, Equity, and Inclusion team, which centered transgender and non-binary voices to measure biases in open language generation. All right, so here's what to expect. A brief breakdown here. You'll get two things from me today. You'll get a talk on, one, constructing a harm evaluation framework that expands otherwise gender binary-centric approaches to understanding gender inclusivity, and here's that outline. But two, you'll also get a talk about the praxis of the AI researcher. Throughout this project, I kept asking myself, what does it look like for an AI researcher to operate within this task while pivoting the default gaze of the AI researcher from one that is otherwise techno-deterministic by training towards one that is more socio-technically oriented. Here, I think, is one of the resolutions in the creation of AI that I'd like us researchers in the room to think about more. Each of us has power and a responsibility to consciously grapple with how model artifacts operate within its socio-technical ecosystem if we are to build towards fairer, more equitable AI systems. And so to do this, as we move throughout the presentation, I'd like to flag key points that impacted my choices in design, be very transparent about that and how I translated that as a researcher to a large language model kind of harm evaluation framework, indicated by this little sign on the right, little exclamation point. So most critically, here the decisions where I chose not to do something were just as important as the decisions where I did choose to do something. And moving forward, some slides I'll go deep on, but other ones I might just touch upon to just keep moving, because there's a lot of content. Okay, cool. So let's get started some more. All right, so here's what we know. We know that LLMs, large language models, can propagate harmful societal biases from the data it's trained on. Several scholarly works, many made by scholars at this very conference, have discovered how models are able to propagate unwanted associations, denigrating comments toward marginalized populations or originating from the data it is trained on. Now, we also know that the trans and non-binary community disproportionately face discrimination, exclusion, violence in daily life. This is ever so present and felt today. Knowing this, gender minorities like the trans and non-binary community are at risk of further marginalization by AI. And also moving forward, as I continue this talk, I'm going to use the TGNB acronym as a shorthand for the trans and non-binary community. All right, so as AI researchers interested in building gender-inclusive LLMs, we first ask, one, what harmful social attitudes towards gender minorities, specifically the trans and non-binary community, should we be vigilant of and assess in our language models? And how does that differ from gender binary perspectives in harm evaluation, right? And then second, do these harms persist in open language generation? So from this, we build out a harm evaluation framework critically informed by harms faced in social reality, explicitly those that differ from the gender binary. We go through an interdisciplinary analysis of our results and release a data set of prompts used to evaluate our models, called Tango, because it just beat like that. All right, so cool. Glad everyone's still with me here. So how do we ground, what am I doing, right? What is the purpose of this? How am I even making sense of this? How do I know something is valid, right? These are questions I'm consistently asking myself questions, right? Am I doing this right? Does this actually even align with social reality? And so here's how I'm approaching this, and I'm being very transparent about my translation. So there are multiple data sources, right? First step, where's the data? Multiple data sources here and options to consider when working with documented experiences. We can either immediately collect the data ourselves, called primary data gathering. Perhaps release a survey, incentivize with some monies, and this is something I see happening more and more in the CS community, and that's great, and it's really exciting. Or we can also first look outside of CS to other domains that have already gathered qualitative experiences with similar inclusion criteria, called using secondary data. So we take this second approach and ground our evaluation by this work on the right-hand side by Jay Puckett, who gathered 181 narratives to understand marginalization stress in this work called Systems of Cissexism and the Daily Production of Stress for Trans and Gender Diverse People. And so this was published in the International Journal of Transgender Health. And a little exclamation point here, and I'll also say ojo. This is something in Spanish where it's like ojo means like eye. You know, it's something that like people would use to be like, watch out. So ojo. For some context, gender minority and marginalization stress have been thoroughly studied and connected to real life. Negative mental health outcomes such as, trigger warning, depression, anxiety, and suicide are very much correlated to these marginalization stressors. So in this work, this marginalization stress is what I define to be a harm, and I'm choosing to translate this into LLM harm evaluation. Okay, so this, right, goes into it a little more. So in the paper, you know, I end up gathering several experiences, these harms specifically, so some things that, you know, were evaluated and found from these narratives are the use of gender non-affirmative language, body policing, such as the evaluation of someone's gender. And this, you know, for example, may look like someone fixating on someone's genitalia to find out what their true gender is, and the outright rejection of someone's gender identity. So now, as AI fairness researchers, now we're studying the context a little more. We're like critically inquiring. Okay, now we move toward the LM harm evaluation design to see how we approach this. And the decision I'm making here is decision I'm making, right? I'm choosing to examine LLM misgendering and responses to gender disclosure, right? Okay, cool. So to be clear, to be very, very clear. Oh, my computer just went somewhere. I'm sorry. Pause on the time, please. Okay. You can reset the time. Okay. So just to be very clear, right here are some failure modes that I'm looking for. On the left-hand side is the first failure mode, which is misgendering, where the underlying text is a prompt used to trigger a model to generate text, and the non-underlying text is the generation. So in this example, Jessie, who uses the pronoun they, is misgendered because the model proceeds to generate pronouns for Jessie that are not consistent with their self-identification. And on the right-hand side, 2 minutes left. Wow, time started. Okay, 2 minutes left. Okay, all right, we're gonna go through this thing. On the right-hand side, it ends up being that the failure of the LLM also can look like negative responses to gender disclosure and body policing. The 2 minute, I timed out my thing to be 10 minutes exactly, but I'm gonna then speed through this. I'm so sorry. We could talk about this after. It is unfortunate. But you know, we end up, these prompts need to be gathered by somewhere. We use the non-binary wiki. I connected with the founders. They're awesome. We have some, understanding of how exactly we chose to do this. One of them being clear indicators as to educational banners that point to, sorry, I'm like kind of panicking right now. I'm sorry. Thank you. Okay. Okay, so we, instead of choosing Wikipedia, basically, we're choosing a trans and non-binary centric community for the text that we're prompting on. So, misgendering measurements, we can imagine gathering some templates, perturbing referents and pronouns, using singular they, using neopronouns. I'm gonna just like walk through this again. We're going through it. Afterwards, we're gonna populate those referents. We're using different kinds of names based on the TGNB Wikipedia. We're gonna evaluate models such as GPT-2, GPT-Neo, alternative to GPT-3, and OPT and ChatGPT as well. And then we're just gonna literally evaluate that with some tool and human annotators. Here's the data set. Check out our paper for more information. We talk about the evaluation tool, how we did that. Long story short, super low neopronoun recall when it comes down to Allen NLP, Hugging Face, and Stanford NLP. So we approached it by grabbing the first pronoun after generation to link back and evaluate against the prompts. And from that, we found literally that misgendering occurs least with referents using binary pronouns. It's significantly more frequent with those that use singular they, and even more so with neopronouns. ChatGPT kicks everyone's butt, but the disparities are still there between singular they and neopronouns. We repeated it across various sizes, and this is consistent still, regardless of model capacity. We did some cool pronoun analysis here. Turns out that models, even still, there's this binary dominance of gender masculine language specifically, regardless of the pronouns that you prompt with. And there's hints that the models can operate in a very grammatically incorrect way with neopronouns. I'm gonna go skip over gender disclosure. It gets really cool. And long story short, we were extracting ways that, and I hate the term extracting, ready? Curating, okay? Different ways that people were coming out or being expressed, their gender identification was being expressed in the non-binary wiki. So for the example, Pandora Box came out as gender fluid, right? Is in a way, in addition to saying someone is this gender. So we were kind of gathering all these different ways that you're expressing gender in language to then evaluate, and I go into this kind of like, other kind of approach, or just talking about this a bit more, but that's the main spiel around like, we have to be careful about how we're curating these things. And so we choose to use this specific kind of self-identified form versus a direct quote for fear of misrepresenting them. Okay, long story short, we end up gathering different forms, and now we're like, cool, well, how do LLMs actually respond to this? And I'm just gonna go through, ready? Check out the paper for the data set. Yeah. Here's what we see. I'm just gonna throw this on right now. Let's go for it. And this is like super close to the end, my friend. Thank you for your patience. Okay, bet. So, figure on the left, what's happening? Here's a ratio of toxic texts produced when using different gender identities in those prompts that we extracted from those and how they were disclosing their gender. We find disclosures with TGNB identities scored most toxic on average if I just said a person is gender fluid. And this is consistent across both static and dynamic forms, static being someone is this gender versus mainly uses the label or came out as or lives as a non-binary person. And so this is consistent where literally the ways that people are disclosing their gender and gender identities are still perceived as more toxic. And so I just point out to attention to explore, for example, you need to be mindful of who the annotators are when looking at Perspective API, obviously. And we don't really know, correct me if I'm wrong, I'm not sure about the information in terms of the distribution of these communities, of who annotate. But at the end of the day, here's what to take away here. Oh yeah, last bit. This was really interesting. After I was looking at all the generated text and I was looking at the most toxic text specifically, check this out. I thought this was really interesting. There were examples of body policing in the generations. The table here provides an example. So when I triggered OPT with Cypress is gender fluid and, it actually generated and has a penis. I'm not sure if you're being sarcastic, I'm just saying that gender fluidity of Cypress is a bit of a stretch. And I was like, oh my gosh. So in fact, I literally went through each toxic example that pertained to TGNB identities and found that these generations contain significantly more references to genitalia than when triggered with man or woman. So what to take away, driving it home, is literally, yeah, we're consistently observing misgendering and negative responses to gender disclosure. And we know with the model, we can consider in context learning approaches and training with more diverse data that incorporates neopronouns. But also, assessing TGNB harms in LLMs requires understanding not only how such identities inherently differ from the gender binary, but also how a framework scope is directly conditioned on who it was made for. So we urge fellow AI researchers to first learn about the community-specific social context to inform and guide LLM harm evaluation. And secondly, we urge researchers to proactively exercise sociotechnical vigilance by contextualizing each of these decisions in the sociotechnical ecosystem it is meant to be deployed in. Thanks, y'all. Thank you for the patience. Okay.
Great job. We have time for maybe just one quick question, if we can do that quickly. Yes, go ahead.
I was just very curious about the term socio-technical vigilance that you put at the end. So I just wanted to hear any sort of practical, any practices that fall under that umbrella.
Yeah, sure. Shameless plug. There's this really, we're actually, there's this work that actually Arjun, myself, and someone else, Vagrant Gautam, we ended up working towards thinking about intersectionality, actually, in how that pertains to AI fairness and praxis. And so coming to socio-technical vigilance, what I think about practicality is, gaining, continuing to build out this framework of understanding that, like, you are like the stuff you do and what you're creating is critically informed by something, right? And we can ask ourselves, what is that something, either through like reflexivity approaches of like, this is what I value, right? We see a lot of these like value system papers coming out, but also we can be critically asking these communities, what are you experiencing? And how can that drive what I'm doing? And yes, we have these like tensions, right? Of like, okay, like, it's, incentives are not as aligned to like participate, gather communities. Okay, there are several ways for you to gather information. Do better, So that's my answer.
Thank you. Let's thank the speaker again.
Okay.
Now we have Myra Cheng presenting on easily accessible text-to-image generation amplifies demographic stereotypes at a large scale.
Hi everyone, I'm Myra. I'm part of a large interdisciplinary team studying what is encoded in text-to-image models. And two, I think, other members of my team are here today, Eileen and Ria. And so any of us would love to talk about this paper if you're interested or have more questions. So yeah, with that, I'll get started. So it is rapidly becoming common for millions of users to use these models by typing in prompts and then receiving custom-generated image. So prompts might include things like a happy family, a taxi driver, an American man in his house, an African man in his mansion, a disabled woman leading a meeting, a kitchen, the face of an attractive person. At this crucial moment in which these models are mass proliferating, our team set out to illuminate the extent and mechanisms by which easily accessible text-to-image generation may be amplifying a variety of historical demographic stereotypes at unprecedented scale. In this case, you see that these models have translated attractiveness to nearly exclusively pale white skin, straight hair, and sometimes unusually blue eyes. So our first goal was to catalog this huge variety of prompt types, some like this and some very different, that all elucidate images with historical stereotypes. So what we found in our paper is that a huge variety of prompts produce these historical stereotypes. This includes prompts that are trying to avoid identity markers, those that explicitly include identity markers, and even just the mere mention of objects. And these problems aren't eliminated by prompts where we're carefully writing them to avoid stereotypes. And they're also not eliminated by the guardrails that some models have tried to put in place. Before we go on, a note about our methodology. Another goal of our team was not to merely demonstrate this evidence, but also to really highlight these produced stereotypes in an impactful way. So our work is really trying to foreground these qualitative exemplars. So what we do in our paper is we're presenting a variety of prompt types, as well as the example prompts that we feed to the model, as well as random examples of the images that are produced. So by emphasizing these qualitative exemplars and including, quantitative analysis when it facilitates understanding these trends, we're really choosing to do this because there's existing literature showing that these qualitative exemplars of social harms and exemplifying imagery are often actually more effective than quantitative means in creating risk consciousness and motivating protective action. Another goal of our methodology is to be translational across various disciplines, so translating across computer science, sociology, and humanistic disciplines. So throughout, we're going to describe some computational methodologies, but we're also going to connect each of them to cases of stereotyping, sociological, and humanist literature. And moreover, all of our work is very tied to this large, long-standing body of psychology literature, which shows that when people are repeatedly exposed to stereotypical images, regardless of whether those images are real or fake, that has really negative outcomes in that discrete social categories are reified, and these images will predict anxiety, hostility, and justification of outright violence. Before we go on, just a warning that the remainder of this talk is going to have quite a few examples of model-produced images that might be offensive or upsetting. So to begin our catalog of prompt types, we first consider a question that many might ask. By using so-called neutral prompts, am I really going to perpetuate historical biases? So we explore a series of such prompts. The first category is those that just only contain single adjectives or like character traits, and immediately we already see stereotypes. So like, for example, the example in the previous slide where attractive was very tied to white ideals. Similarly, we see that exotic is very associated with features that are exemplified or associated with women of color, non-European adornment, Afro-ethnic hair. And this is connected to a long history of the othering, sexualization, and dehumanization of these groups. Similarly, the prompt "a poor person" generates faces with dark skin tone and features that are stereotypically associated with blackness, which perpetuates patterns that are known to invoke hostility and violence against people perceived as black. And finally, one more example we put here is that prompting for a terrorist generates brown faces with dark hair and beards, consistent with narratives that have been used to rally for anti-Middle Eastern violence. Another question we explore is how these prompts might facilitate stereotype amplification. So by amplification, we mean that a particular trait is much more associated with a particular group than the real-world correlation. And so we actually find evidence of near total stereotype amplification. So for example, based on US labor statistics, around 56% of software developers reportedly self-identify as white in the US. However, in the generated pictures, 99% of the generated software developer images are represented as white. There's quite a few subtleties to quantifying these patterns responsibly, so we welcome you to read the paper if you have any questions. So based on the prompts so far, you might still think if we use only prompts that describe objects, we can still avoid biases. But actually, we find that stereotypes and norms are also in images that are just only of everyday objects. So for example, we generate a bunch of images using the prompt front doors, and then we also generate images using the prompt front doors in North America, front doors in other continents, and we find that just the prompt front doors generates images that are a lot more similar to the North American ones and extremely different from the ones that are front doors in Africa. So we connect this to a perspective that people have called the view from nowhere, which means that despite it being clear that the model has a very specific perspective and set of assumptions, all of these things are being completely hidden under a guise of neutrality, and this facilitates the exclusion of marginalized perspectives. And next we're gonna look at, okay, so those are all like no identity markers, no explicit mention of demographics. Now, even if we do explicitly put the identity markers, it might not surprise you that we still continue to see stereotypes. So here we see that the image of the Iraqi man and related objects are like more worn down or related to war and military force, while those associated with an American man are much more shiny and new. And these patterns continue for a host of other identity markers. So finally, this brings us back to the question of correction. What if we are using prompts that explicitly contain anti-stereotypes? And we find clear evidence that this actually doesn't eliminate any of the stereotypes. So for example, to try to counter the pattern that links blackness to poverty, one thing that we tried is using the prompt "a poor white person." However, we still get images that have dark skin tone and stereotypically black features. And this reveals how the model is fundamentally unable to disentangle this correlation. And so a lot of the more recent mitigation methods, which are focused on prompt engineering, are not very effective. And a final strategy to mitigate bias is to use models with guardrails, such as DALL-E. And so while some issues are addressed by guardrails, for example, you might get like a different range of skin tones for a particular prompt, we still find many cases of the same harmful patterns. And this is in part because of the sheer complexity of these stereotypes. So it's impossible for model owners to think of, let alone correct all such associations. So for one example that we put on the slide, if you ask for the prompt, a disabled woman leading a meeting, you get an image where the visually disabled woman is still not leading the meeting, but instead listening. But instead, if you prompt it with a blonde woman leading a meeting, you do get exactly what you want. So this problem is unique only to like marginalized groups. Yeah, so in summary, our paper demonstrates that there's a wide variety of harmful stereotypes that are being mass proliferated by these text-to-image models. And these stereotypes have been connected to dangerous narratives that lead to exclusion and domination over marginalized groups. Our analyses shows that even carefully curated prompts cannot solve the problem because these images encode and display a multitude of information beyond the specifications of what's explicitly written in the prompt. And so we cannot prompt engineer our way to a more just, inclusive, and equitable future. We believe that mitigation requires moving beyond these reductionist approaches and examining the evolving power dynamics. And we're calling for users, model owners, and society at large to take a critical view of the consequences of these models. The examples and patterns that I've talked about here and that we demonstrate in our paper make it clear that these models, although there's a lot of hype and they really appear to be unprecedentedly powerful and versatile in being able to create images of things that might not exist in the real world, they're actually really brittle and limited in the worlds that they can create. Thanks for listening.
Do we have any questions?
Thank you for this amazing piece of work. Kind of a specific question about the anti-stereotype prompts that you mentioned using. Could you say a little bit more about what you observed with those? Was it that kind of like the output still overrode the like anti-stereotype content of the prompt, or just curious to hear more about those results.
Yeah, so I think again, our paper was really grounded in different exemplars. So we just tried different prompts. And so for example, one of the examples being trying to say a poor white person, you still get, we generated 100 images, and a significant portion of that still had stereotypically black features or darker skin tone, even though we specified white in the prompt. Another example is we tried to do things we saw that if you use the prompt an African man in his house, you get all these really bad stereotypes. So we were like, oh, what if we say an African man and his, his huge house, or a wealthy African man, or an African man in his mansion. All of these examples, you still kind of get the same output, which means that, or I don't know, somehow those things are still correlated despite those modifiers. Yeah.
Thanks.
Are there any more questions? I think I saw a hand at the back.
Hi, thanks for your talk. I have a question regarding the amplification you were talking of. You said you took the US statistics as a reference for the amplification. I was unsure whether that's a good reference because the real world is, or the training data is for DALL-E not available, and for stability or for stable diffusion from stability AI is web scraped, and that's more than just US statistics.
Yeah.
So I was wondering, what do you think of that?
Yeah, that's a great question. I think that we have to start somewhere, and there's a lot of work, actually some of it done by Eileen, that a lot of the kind of representations and defaults in visual semantic models and language models are default to American norms, and so that's kind of our basis. But you're right that maybe this isn't a normative thing. Maybe we shouldn't be trying to match this to the US, and there's a lot of nuance there, but it is a starting point because no matter what statistics that you're using, it really shouldn't be 99% white, right? I think we can agree on that.
Any more questions?
Yeah, thank you so much for the wonderful presentation. So you mentioned a couple of times in the presentation this concept of eliminating bias, or kind of moving away from less biased representations. So I'm curious what that would look like to you. I guess a lot of these things could be stereotypes, and there's no way to obviously create like an extremely neutral, completely bias-free kind of representation. Is that like a fundamental like validity problem with the models to begin with? Yeah, I'm just curious what your thoughts are.
Yeah, that's a really good question, and it's something that I've also personally been thinking a lot about because I feel like I've been doing a lot of work on like, here's all these problems. And I think that right now my answer is like, first of all, it's like I feel like it's a big open question, and then also like it definitely I think shouldn't be worse than kind of like these real world biases. So at the bare minimum, we shouldn't be amplifying things. And also I think that there's like a lot of to be said about like, oh, people should be aware of these things rather than just blindly using them. Especially, so like I feel like it's like, oh, there's bias in any model, but it really becomes important to think about these implications when these models are being mass proliferated. Yeah.
Okay, if there are no more questions, then let's thank the speaker again.
Thanks.
Next, we have Prakhar Ganesh presenting on the impact of machine learning randomness on group fairness. And once you go ahead, I'm going to present you with the Best Paper Award because they won the Best Paper Award. Are you taking a photo? Can you see my hand? The Best Paper Award.
Thank you. Hi everyone, I'm Prakhar, and today I'm presenting our paper on the impact of machine learning randomness on group fairness in collaboration with Hongyang Zhang, Martin Strobel, and Reza Shokri. So let's just jump right into it. As we are all familiar, machine learning has a fairness problem. And one of the biggest pillars of fair machine learning is our ability to be able to evaluate and empirically talk about bias present in a model. However, a bunch of recent work has shown that fairness can change significantly by just changing the randomness in model training. And this is the central question that we'll try to tackle in this paper. So let's start with a very simple example to understand why randomness has such a big influence on fairness. So we'll talk, for the rest of the presentation, when I say fairness, I'm just talking about average odds. And also for the rest of the presentation, I'll be discussing my results on a tabular data set called the ACS income data set. I'm sure a lot of you are familiar with it. And we'll be training a simple neural network on top of it. While training a neural network, we can do a lot of things. We can train it unconstrained, just like a standard training, which we'll call the baseline training. And we can also do a lot of bias mitigation methods. You don't really need to know what they are, but let's say we want to figure out which of these methods is the best method for bias mitigation in this particular setting. So let's say we train 4 models, and we get these fairness scores for these models, and we decide, okay, maybe equalized opportunity loss seems to do the best. However, if we run the same exact experiment again by just changing the randomness in training, we get a different set of results, and we might say, no, maybe fair batch is a better option for this setting. We repeat it a 3rd time, and now we say, fair batch does do better, but it has a huge variance, so maybe we should stick with equal opportunity loss. In other words, there's a huge variance in fairness scores across different random seeds, and making any claims or extracting any trends from for fairness without actually capturing this distribution can be really bad. Existing work which point out this issue tend to do a very naive approach to solve this problem, which is just execute multiple training runs. You have a fairness variance, so you just run the model, train the model 50 times, and you'll get the distribution that you care about. Of course, that's not good because, one, it's extremely expensive, and that just gets out of hand with bigger models. Second, it raises the bar to do fair machine learning research. You have a model whose accuracy you want to capture, you just train a single model, but if you care about biases, you need to train 10, 20 different models. And finally, it lacks an understanding of what really is happening underneath it. Why is it that fairness is so sensitive to the randomness in training? And this underlying cause is what I hope I'll be able to explain today. First, let's start with different sources of randomness that are present in any machine learning training pipeline. We'll talk about two main canonical sources of randomness, which is weight initialization and data reshuffling. First, when we start training a neural network, we start by choosing an architecture that we want to train and then initialize the model with a random set of weights, usually from a predefined distribution. That's the first source of randomness that gets introduced in the training pipeline. We then take the training data and shuffle it and create batches. We do this to simulate what we call stochastic gradient descent to train a model. And the data gets shuffled and reshuffled at every training epoch to simulate this stochastic behavior to get the final trained model, which is where we get the second source of randomness in our training. The final model is then evaluated on a test data set, and you can measure fairness, accuracy, and so on. For the rest of the discussion, to kind of figure out which source of randomness is really the culprit here, we are going to talk about two specific settings. Number one, we'll train a bunch of models with different initializations, but we'll keep the random reshuffling fixed. In other words, we'll feed them the same data order. And in the second setting, we'll start them with different weight initializations, but we'll feed them we'll start with different weight initializations and we'll feed them the same data order. So we want to see exactly which of these sources of randomness truly affects the fairness variance. So we create these two settings, and we want to measure the fairness scores across during training for these two. As we start executing multiple training runs under these two settings, you'll start to see a pattern emerge. On the right, when we start models from the same initialization but feed them different data orders, it becomes really messy. For at any particular epoch, the fairness scores have a huge variance. However, on the left, when we start models with different initializations but feed them the same data order, you can see that the training curves seem to overlap with each other. In other words, even though there is huge volatility in fairness scores across consecutive epochs, the fairness scores across multiple training runs at any one epoch is very small. We repeat this for 50 training runs, and instead of actually plotting them all, we just plot the distribution, and it just reflects the same observation it made previously, which is essentially that the data order that we feed to the model during training has a huge influence on the kind of fairness that you'll get in your model, while the weight initialization is not so significant. Next, we'll take a step back, and instead of talking about randomness, we'll try to figure out why is it that fairness scores are so sensitive to minute changes in model weights which get introduced due to randomness. To do this, we'll calculate the prediction uncertainty of different data points in the data set using a method called the Monte Carlo dropout. I won't really go into the detail of how this works, but essentially the point to take here is higher uncertainty means the data point output can change very easily with minute changes in the weight. The data set that you are working with is the income data set, and this is a demographic distribution of the data set. We'll focus mainly on the minority group here, which is the positive labels from the perceived gender group female. We'll plot the prediction uncertainty distribution, the cumulative distribution of prediction uncertainty for each group separately. We want groups to be at the left top because that means most data points from that group have very small prediction uncertainty. In other words, the evaluation for those data points is going to be quite stable across different random seeds. As expected, the minority groups tend to be on the right bottom side. That is, a huge percentage of data points from those groups have very high uncertainty, which in turn makes them vulnerable to changes in evaluation in accuracy as the model weights changes, which in turn affects the fairness scores. Finally, so we have some understanding of why there's such high sensitivity of fairness scores to changing randomness. And we understand that data order plays a very significant role in the fairness score of the final model achieved. We'll try to use that to come up with some applications. The first thing, we go back to the question that we started with. Can we talk about fairness distribution across multiple training runs without actually executing multiple training runs? So we'll talk about variance on two different axes here. Variance across training runs, which is you to execute multiple training and you measure the fairness at the end of the training. And variance across epochs, which is you execute a single training run, but you measure the fairness score at the end of every epoch. As expected, as we saw earlier, the data order has such a dominant influence on the fairness scores of the model. The left three distributions are the distribution of fairness scores across multiple runs by just at any particular epoch during training, while the right three distributions are the distribution of fairness scores across the training in 3 separate training runs. Even though the right distributions are 50 times computationally efficient, they help us give us a proxy to understand the distributions on the left, which is what we really wanted. The second application is, now that we know that data order has a dominant impact on fairness, can we create our own data orders to steer the fairness scores in whichever direction we want? I won't really go deep into how we create the data order. Please check out the paper for that. We talk about 2 special data orders here, a good data order, equal order, which aims to achieve fairness, and a bad data order, adversarial order, which aims to introduce extra bias. Again, we train a model unconstrained, and we record the average odds, the fairness score, and the F1 score of the model. We then take the converged model and continue the training for just a single epoch with our custom data orders. And we see that in just a single epoch of additional training, using the data order that we created, we are able to significantly reduce bias or significantly increase bias in the model with relatively little impact on the F1 scores. So just to quickly conclude the takeaways from this paper. First, we talked about how data reshuffling is the dominant cause of fairness variance that we observe in literature. Second, we talked about the high sensitivity of underrepresented groups to randomness in model training, which in turn gets reflected in the fairness scores. Third, we talked about how fairness distribution across multiple runs, which is something that we want to figure out, can be calculated by using a proxy, which is fairness variance across multiple epochs in a single training run. Finally, we talk about how just by controlling the data order, we can very easily manipulate group level accuracies and fairness scores and then steer them in any direction that we want to. Due to the nature of the presentation, of course, we talked about just a single data set, a single fairness metric, and so on. But we talk about a diverse set of experiments and a lot of experiments that I couldn't cover here in our paper, so please feel free to check it out. Yeah, thank you.
Thank you for the great talk. Do we have any questions?
Hi, thank you. That was it sounds like really interesting work. I was curious, did you only look at the single fairness metric, or did you look at like whether different metrics are like doing better or worse at different times?
So we looked at a lot of different metrics, and the idea is essentially because the underrepresented groups are far more sensitive to minute changes in model weights, their accuracies, whether you talk about, say, average odds, which looks at true positive, false positive rates, whether you directly look at accuracy disparity, or any other metric, their accuracies always tend to be far more sensitive to changes in randomness. So any disparity calculation ends up being equally more sensitive to changes in randomness. So yeah, we do talk about various matrices, and they all more or less have similar issues. And that's because at the heart of it, the minority itself is quite sensitive to just a change in randomness in training.
Well, I have a question. So you said you conducted more experiments, and I'm really curious about what happens to this randomness as the feature size increases of your data problem? Like, for instance, the adult data set has a specific set of features, right? And I'm wondering if it's like growing exponentially or linearly with the size of the data.
So we also played with Celeb A dataset. It's a vision dataset where essentially you want to, it's still a classification set, and it has a significantly bigger feature size. We don't really see any patterns of increase or decrease in variance with feature size. We see similar variance in fairness scores as we saw in this dataset. It's just the absolute values, of course, change. Like instead of, say, fairness variance from 0 to 10, in Celeb A, we see fairness variance from, say, 5 to 15. But it's more or less same. There's no obvious pattern, really, with like feature size. Although we do look at only 2 data sets with different feature sizes, so maybe there is something. But yeah, we didn't observe anything like that.
Thank you. Are there any more questions? Okay, in that case, we should thank the speaker again. Next, we have Cyrus presenting on detection and mitigation of algorithmic bias via predictive parity.
Sorry, I'm Brian.
Oh.
Yeah.
Oh, okay. My bad.
Cool. Oh, I talking to this mic. Hey everyone, thanks so much for sticking around to the last presentation. My name is Brian. I'm an AI engineer at LinkedIn, and today I'll be going over our paper, Detection and Mitigation of Algorithmic Bias via Predictive Parity. And so it's really exciting to share this because this is the actual fairness definition that we use and measure at LinkedIn for our AI models, for binary classifiers mostly. So it's great to share this, and I'd be really interested to also continue further conversations about whether this metric is good, ways to mitigate it, and et cetera. So the high level is I'll give a description of this metric and give details about how we are able to modify it to handle when we have dependencies between samples and some extensions of that. So first of all, what even is predictive parity? Well, mathematically, the definition is that you want your labels or outcomes to be conditionally independent of the group given the score. And the way that I always like to think about it is if you have a binary classification model and its score is something like 0.6, you want that to have the same interpretation in terms of the expected outcome, like click-through rate or the click probability, regardless of who is being scored. And so you can imagine that this is really useful in several applications, including healthcare. You know, if you have a disease screening model, you want the output to mean the same thing regardless of who is being scored. It's also useful when you have downstream applications or in marginal outcomes testing. It's also a fairly intuitive notion of fairness that's been around for a while that we like to use and aligns with traditional modeling objectives like MSE and AUC as well. So I'll give an illustration here using 2 genders, male, female. Gender is, of course, very diverse, and this methodology does generalize to non-binary and intersectional groups as well. But for example's sake, let's say you have a machine learning model and it produces the same score for 2 people. In this case, it's producing a score for a female that's well calibrated, which is to say that the expected outcome aligns with the score. So it predicts 0.85, means empirically there's an 85% chance of being clicked. But it's not well calibrated for males. So it's predicting 0.85, but the actual click probability is much higher. So when we go and rank these people in a recommendation system, there's going to be bias in terms of who gets more exposure, because even though the scores seem similar, the empirical qualifications are different. Okay, so what exactly do we want to do here for measurement purposes? Well, predictive parity requires that the conditional outcomes is the same given the score across different groups. And this idea is closely tied to calibration in the sense that essentially you violate predictive parity when models are badly calibrated for one group versus another. And so really what we want to do is be able to measure the differences in the conditional expected outcomes given the same score. And so traditional methods, such as using binning to measure the conditional outcomes, are known to be statistically biased. And there's several works that try to measure the overall calibration error for each group, but this doesn't directly tie to the measurement that we're interested in, the quantity, and therefore it doesn't exactly tie to the fairness issue at hand either. And more importantly, these methods don't handle potential dependencies between samples. And so what do I mean by that exactly? Well, there are some instances where certain individuals contribute multiple samples in the data. For example, unlike me, if you're popular at LinkedIn, then you tend to get more clicks. And you have to ask yourself, like, do you trust that one person should be representative multiple times in the data? And it's a similar story in disease testing scenarios where maybe more affluent people can be represented in the data set more frequently. And so what I have here is an example to show that these two assumptions can lead to vastly different readouts. In the graph on the left hand, you see I have 50,000 individual independent samples, and I'm computing the expected outcome on the y-axis and the scores on the x-axis. And in the graph on the right-hand side, I'm taking 10 individuals, which is far less than the 50,000 originally, but I'm going to duplicate their observations by 1,000 times each. And so I've messed with less than 1% of the unique individuals in the data, but it vastly skews the fairness readout because those individuals happen to be unrepresentative somehow. So that illustrates the problem of testing under dependency versus independence and why it's important to make the distinction. So the main technical contribution of the paper is a modification of the Nadaraya-Watson kernel estimator to do exactly that, account for the dependency structure. And intuitively, basically, instead of one level of aggregation across all users, we're going to aggregate within a user and then across all users. And so there's some theory in the paper that has some nice results like asymptotic normality and the estimates. But more importantly, this lets us measure the exact fairness definition of interest. And we show multiple applications of this, like non-parametric calibration, marginal outcomes testing, and testing for multi-objective models. And I want to harp on that last point a little bit because we think it's quite interesting. So oftentimes in industry, when you have a model score, that's not the end of it. Because oftentimes it's used in a downstream model, and in such a case, you would want this kind of property to make sure that the score as a feature has the same value regardless of who's being scored. But another instance is you're using it for a multi-objective optimization model in the sense of, like, say you want to optimize for both sessions and click-through rate. And so in such a case, what can you say about predictive parity? And it turns out we can actually say something if the multi-objective optimization model is linear in the sense that it's a linear combination of the scores from different models. So essentially what you can do is actually calibrate the component scores by replacing each of them with the expected outcome estimate from a multivariate kernel estimator from the joints, using the joint scores as the features. And then you can get a composite score which will satisfy predictive parity. So to just illustrate this high-level process, essentially, if you have different models producing different scores, you can aggregate them, calibrate them, and then when you have the same predicted score for individuals, you can expect that they have the same conditional outcomes regardless of the group. So that's a nice property to have, and in general, this idea of fairness under component models or composite models, I think is an interesting research topic for the future. I also want to say more about what this metric means for us at LinkedIn, because this is actually the metric that we use to measure our models. And so what you see on the graph on the left hand is actually the readout for a model that generates profile recommendations when you go to a member's page. And indeed, when we were analyzing the model based on this exact methodology, we found gaps in predicted parity fairness. So in another paper, Disentangling and Operationalizing AI Fairness at LinkedIn, also here at FACT, we basically go through a case study of how we did this measurement, what processes we took to mitigate it, and what we did afterwards to make sure that it didn't cause any unintended harm to our members. And it was a great result because we saw improvements in both fairness as well as product metrics when we actually launched an experiment online. So that's all I have. Thank you all so much for your attention. My name is Brian. If you have any other questions or want to discuss this more, please reach out to me through your favorite professional networking platform.
Thank you.
All good.
Do we have any questions?
Hi, thanks for the talk. Can you elaborate more on like what predictive models these like fairness things are actually being used in?
Yeah. So like some examples of like where this actually matters. Yeah. So like in this case, we were doing the measurement on like the model that generates the profile recommendation tab. Basically, like if you go to someone's profile, you'll see on the sidebar like, oh, people also viewed these people. So like the model that generates that is essentially a binary classification model. So that's an instance where this could be relevant and can also have the same issues of fairness, which is illustrated in that example there. It's also applicable to other algorithms like people you may know. And I think those are a couple of the major ones that we're thinking of right now.
Do we have any other questions? Well, I have a question. So you showed a graph at the end, which showed like how you used it at LinkedIn. And then I'm guessing, did you do an assessment of the implementation?
Yeah.
And then is that what the second graph is?
Yeah, exactly. So the control is like a representation of the bias, and this is all in an actual online A/B test. We collected data from an experiment, had the control model as well as the treated model where we mitigated this bias. And on the left, when you see the gap between the lines, that's a bad thing. That's the predictive parity gap. And so the fact that we're closing those lines together is essentially how a representation that we're making it fairer.
I see.
Yeah.
And what were the groups you considered?
So for here, we're considering the intersection of gender and geography. Yeah.
I see. Also, do you consider like all continents and?
We have like specific definitions of like major countries.
Okay.
Yeah.
Thank you. Well, if there are no more questions, can we thank the speaker again?
Thanks so much.
And that ends the session. Thank you everyone for coming.